Welcome to the demonstration of a buffer overflow attack demonstrated on a Linux machine with x64-bit Intel architecture. So let's get started. What we have over here is a simple C code which will take a command line argument, and we have a buffer over here which is 256 bytes long, and our string copy function will copy the command line argument into our buffer. So this is the basic layout for our attack, and we need to manipulate our buffer such a way that we can run a shell after successfully completing this attack. So let's get started. Now what we need to check is that whether our system has protections enabled. So basically Linux has a lot of protection enabled to prevent such buffer overflow attacks. So first we need to check whether address randomization is switched on. So let's check that in our system, and you can find it over here. So as you can see, mine is 0 now. Initially it should have been 2, so I have changed it with super user privileges. So if it's not there, you need to fix that now. And so basically what this does is we have what is known as ASLR, which is address space layout randomization in Linux. So it randomizes the virtual addresses generated during the execution of a program. So basically when we are executing a buffer overflow attack, we have to guess the return values and where the shellcode needs to be. So that requires a bit of trial and error. So if randomization is switched on, we cannot do that. So we need to make sure that it's off, and as you can see over here, mine is off now. And we need to compile our code in such a way that further protections which are enabled by default is switched off. So I'll explain what these flags are in a moment. Now let's compile it with these flags. Okay, now our program is compiled. So now I'll explain what these flags are. So the -G flag over here, it will help GDB, which is a GNU debugging tool we are going to use now in a moment. So it will generate some metadata. It is used by GDB and it will helpful. If it's not there too, the -G flag, if it's not there too, it will work. So the next flag, which is -Z exec stack, will give us execution permissions on stack. So by default, stack is non-executable. It means that we cannot run some code on stack. It is non-executable memory, and we need to change that so we can run our shell in the stack. Now what the next one is -fno stack protector. So stack, to prevent buffer overflows, stack has a lot of what we call as canary values. So it will those are numbers which can be verified by the system if it's overwritten. So whenever a buffer overflow occurs, the canary values are overwritten, and the system knows that there is some mistake happening in the stack. So we need to switch that off so that we can have stack smash. So that is what they call it, stack smash protection. And so we have switched off that now, and we have basically generated the compile code in hack. So you can see it over here, hack, and we now have to start the debugging tool with PEDA enabled. So PEDA is a Python exploit development assistance. So it is a library which can be downloaded from GitHub. It will enhance the default GDB present in the system. So I have enabled that. Now let's move on to analyzing our compiled code in GDB. Now let's see our main function over here. You can see that this is our code. Now let's set a breakpoint right in the starting of main, just so that when the program runs, we can have a look into how the registers are filled and how the memory is filled. So okay, I have accidentally executed that. So this is bit of code which basically runs our compiled hack code along with the argument, this one. So this is a Python code which will run on the shell, and it will print x41 260 times. So as you can see, we have our buffer defined as 256, and we have now given an argument which is 260 bytes long. Let's see what happens now. When I execute it, the breakpoint is the execution stops on the breakpoint just when the main starts, and as you can see that our RBP, which is the base pointer for our stack, is this address, which is DE10, and we have our stack pointer at DD00. And you can see over here, this is basically how our stack looks when we execute our code. So this will be the buffer, which is 256 byte long, and here there will be our base pointer, and here is the return address, and stack grows towards the top, and in the memory it's actually towards the lower address, as you can see over here. Now this basically means that our RBP DE10 over here will be pointing towards this green block, and our DD00 will be on top of this pink block in our image. So now we are just in the beginning of the main function. Now let's go to the next instruction by instruction, which is through this command ni. So let's move on to our strcopy function, which is right over here, which is the call function in assembly code. Now right after we execute this function, we expect that our buffer takes the argument and writes into the memory. Let's see what happens now when I run this instruction. So as expected, we have our values written. We have 256 bytes written completely, and since I have given 260, we'll have 4 bytes overwriting our base pointer. As you can see over here, our base pointer is pointing to a memory location with 4 bytes overwritten. So this works. Now let's move on to what happens next when I completely execute this. So the leave instruction just after this one will make sure that the RBP is changed, and since the main has completed execution, it will just try to go back to the previous function. So now our RBP is junk. We have changed the RBP which was initially there, and this is the RBP we have right now, which is overwritten by 4 A's. So now basically, if we try to return to that location and try to execute some code, it will eventually break. So right after return, it has gone back to some other instruction executed. So now moving on, let's see what happens when I completely override the base pointer. Now we'll do the same thing with this base pointer completely overwritten. So when I type 264 bytes into the buffer, we have, as expected, it will be completely overwritten with A's. And now moving on into the return, after a while it will break. So since the buffer is since the base pointer points to some other random location we have inserted, it will cause problems when the system tries to access those memory, which is not available to the program. So now let's move on to completing the attack. So what we have is we have written A's starting from the beginning of this buffer, and we have completely overwritten the location pointing the base pointer. So now we need to override the return address. So that is how we execute this attack. So for that we need to find a suitable address location. Now when I execute this instruction by instruction and we encounter this strcopy function, I will just check how the memory is actually filled. So we can use this command examine. So it breaks down to like this: examine 260 bytes of it should be bytes, xg represents bytes, and $RSP will point to the stack pointer. So right after the strcopy function, we should have the A's, which is x41s in hexadecimal, written over into the memory. As you can see, it is over here, and this is a memory location right in the middle of this buffer. So this is basically where we want our code to return to, and we will basically fill a malicious code right over here, and let's move into that later. So basically here is the return value what we want. It should be chosen right in the middle, so that when the execution occurs next, a stack changes a bit, so it might move up or down. So if we choose something in the middle, we should be all right. So let's see how the attack actually works. So basically we'll fill the buffer with a lot of no operation instructions, which will instruct the system to just skip the memory location to the next one. So we have a lot of no op instructions, followed by a shell code, which is our malicious code that we want to execute, followed by a fake return address. So we have found the return address. It should be something over here, and we will have our shell code over here, and the fake return address should be written over here. So once the system executes that, we should have instruction pointer landing over here. It will completely execute the no op instruction, which means it will skip it, then it will move on to the shell code, and we should get a shell. So that is the objective of our attack. Now let's see if we can do that. So before that, we need to find a suitable shell for your machine. So you can find it over here. This is a website that I found on the internet. You can see over here, and based on your system architecture, you can choose a shell. So this right over here, link right over here, it will execute the bins sh, which is a shell, and it is 27 bytes long. And you can see when I click the link, it should open something like this, and you can see the code over here. This is what we want, and I have already copied this into here, and now we have a bit of calculation to do. So we have found out that 264 is the exact value which will correctly override the base pointer. So right after that, we need to insert our return address. So first we'll insert a lot of no op operations, which is represented by x90s, and we have about 200 of them, exactly 200 of them, and we have 27 byte long shell code. So, and after that, we need to make sure that this thing comes to 264, so we can insert our return address over there. So to make it 264, we have to add exactly 37 byte long characters. So we have 200 plus 27, which is 227, plus 37, which makes 64. Now we need to add the return address to our buffer. So we have found the return address over here. I have copied it, and since our Intel architecture is little endian, we need to insert it in the reverse order. So it should be 70 followed by DD followed by FF and so on. So this will be 48 bytes, since our 64-bit architecture uses only 48 bits of address. So if it's more than that, it will cause a segmentation fault. So we need to make sure that this calculation is right, and I have copied the values over here as /x70 followed by ddff, and yeah, as you can see, let's see what happens when we run the code. If everything goes fine, we should have a shell in our hand. So when I execute it, it breaks in the beginning of the main function just because we have a break point there. Now let's move on to the next instruction, and after the call instruction, as we expected, we have values 8 A's in our RBP, followed by what's written in the return address, which is our these values. It's converted. Now after the execution of next instruction, we have the RBP changed. Then after the return operation, we are now in the address that we provided. This is the address that we hope for, and we are right in the middle of the no ops, as you can see over here. And if I click next or set next, there are a lot of no op instructions just as expected, and we have our shell code right after that. So now when I say continue instruction, we have now completely skipped the no ops and we are right in the shell. And as you can see, our shell is now opened, and I have now completed successfully the buffer overflow attack. So if I type a command over here, it will just execute that command and it will quit, since we are right inside GDB. So now we have completed the attack. So just revisiting what we have done, we have found out the return address which is right in the middle of our buffer. We have found a appropriate shell code for our machine. We also have found the exact locations to where these instructions should be put. So let's now execute the attack outside GDB. So I will now run the compile code along with our argument right over here, and it should give us a shell. And now I can type how many commands I want. We have ls, and now I have access to the machine. So basically, if your process is having a higher privilege and you execute a buffer overflow, you will have the root privilege and you will have taken over the machine. So that is how we execute the buffer overflow attack. And thank you for listening. Bye.